Hello, I am Vaibhav Venugopal Rao from Drexel University. In this presentation, I will be talking about security vulnerabilities of obfuscated analog circuit. This is the outline of the presentation. Initially, I will be talking about the need for analog hardware security, different analog obfuscation techniques, and the metrics to evaluate the security of the obfuscated techniques. Then I will be presenting the two techniques that form the basis for evaluating the security of the analog obfuscated techniques. Then I will be providing the design insights and conclusions. In the past few years, there has been increasing demand for the analog circuit. This basically arises due to the development of AI, machine learning, and real-time data streams, and as well as due to the rise of electric and autonomous vehicles, increase in home automation and IoT of things, increasing trends towards the 5G communication and technologies, and use of analog computation to reduce the overall circuit power. This has resulted in analog IC market growth rate of around 4.5% through 2021, while analog revenue is estimated to reach about $63 billion by 2021. To meet the growing demand for the analog circuits, the IC manufacturing companies have shifted to offshore fabrication, assembly, and packaging facilities. Although this has led to a reduced time to market time, it has also increased the attacks on the analog circuits uh, in form of reverse engineering, counterfeiting, and overproduction. So the use of offshore facilities coupled with the greater complexity in designing analog circuit and the greater risk in fabricating analog circuit, lack of EDA, analog EDA tools, and greater reward for the first mover advantage has motivated attackers to attack analog circuits. So due to which the analog IC are the third most counterfeited semiconductor component, and analog IC manufacturing brands are among the most frequently targeted brands for counterfeiting. Mm. To mitigate these attacks and vulnerabilities in the analog circuit, uh, different obfuscation techniques have been proposed. These are of two types, so device-based and key-based. The device-based techniques include the split manufacturing and multi-threshold of obfuscation. So in the key-based attack, it can be of two types. So one is the purely analog circuits, that is the parametric obfuscation techniques, and the other one is for the mixed signal circuit, where digital blocks of the mixed signal IC are obfuscated. Uh, so to evaluate the metrics for the obfuscation, so we consider the example of digital IC. For the digital in the digital IC obfuscation, SAT solvers are predominantly used to evaluate the effectiveness of the digital obfuscation techniques. This includes the number of iteration and execution time for the SAT solvers. The basic inputs that is required for the SAT solvers are the input-output response and the extracted circuit netlist. Coming to the analog ICs, there are two types of metrics that solvers that are used to evaluate the security of the analog circuits. So they are the SAT solvers and the SMT solvers. The SAT solvers can only be applied to the mixed signal circuitry where the digital obfuscation techniques are used to obfuscate the mixed signals. But for the SMT solvers, the designer requires in-depth in-depth knowledge of circuit specification as well as detailed analog circuit equations and models. This shows that the metrics to evaluate the analog obfuscation security is not as robust as compared to digital circuit, wherein the designer requires in-depth circuit and specification information, and different metrics are used to evaluate different analog obfuscation techniques. So in this paper, we propose a unified security evaluation metrics for key-based analog obfuscation technique. In this section, I will be talking about the security vulnerabilities that exist in the key-based analog obfuscation techniques. So this is an example of a parametric obfuscation technique where the transistor M2 is obfuscated, and only when you obfuscate, only when you input a correct key, correct the size of the M2 is selected, which produces a required target gain. So if an incorrect key is applied, an incorrect M2 width is selected, and therefore the gain of the amplifier is not as intended. So with that in mind, the current key-based obfuscation technique has two main weaknesses. So one is the key spacing. This is a presence of exclusion zone around the target key. So this is in place to ensure that an incorrect key produces a significant degradation in the circuit performances compared to the target key. The next one is the monotonic response. So here the transistor with M2 um, is produces a gain response as shown in this figure. So the gain here is a monotonically decreasing function with respect to the transistor width. So these two knowledges can be used to evaluate the security of the analog obfuscation technique. So I will be talking about the key spacing attack in this section. Um, the, the, the main premise of the key spacing attack is that the obfuscation transistor requires an exclusion zone around the target device dimension. That is this. This is required to ensure that the incorrect key produces significant degradation in the analog circuit performances. The threat model for this attack is that the adversary possesses the circuit netlist, which is used for targeting the obfuscated transistor sizes, but the attacker does not require an oracle response. So for the preliminary evaluation, so from this analog circuit netlist, all the obfuscated which information are used, are combined in the. So this has been included in the set WV. So based on the set WV, all different combinations of the bits have been calculated and is inputted into a set SW based on the equation. Before the start of the algorithm, the user provides an exclusion zone, which is a guessed value of the expected exclusion zone around the target width. So the algorithm starts by picking a random width Wi from the set SW. So in the next stage, it calculates another width WA, that is the next nearest width from WI. So then if WA minus WI is greater than or equal to WI times the variation, then WI is considered as a candidate width. So once the WI is considered as a candidate width, then constraints are added such that the two widths are excluded from the search space. So if WA minus WI is less than WI minus variation, then WI is not a candidate key, and then the constraints are added to exclude WI from the search space. So the algorithm determines all the candidate widths in the search space and returns the list of all the candidate widths at the end. So the key spacing attack is evaluated on 4 different circuits and with different exclusion zones. So from the results, we can see that an average of 5 candidate keys is done in an average of 4.5 seconds, and we can see that the attack is more efficient for greater variation since large amount of keys have been eliminated per iteration. So the time to solve exponentially increases with the key size in this attack. In this section, I will be talking about the monotonic circuit response attack. In this attack, the monotonic relationship between the key and the circuit response is evaluated. For the example of a CS amplifier shown in the figure, the transistor width versus the gain is evaluated, which is a monotonically decreasing function. The main premise of the attack is for a randomly selected width, the circuit response produced by the width. If it is less than the target width minus a certain variation epsilon, then the algorithm knows that the selected width is too large, and constraints are added to look for the width that is less than the guessed width. And similarly, if the randomly selected width produces a circuit response that is greater than the target value plus an epsilon, then the algorithm knows that the selected width is too small, and the constraints are added to look for the width that is larger than the guessed width. The threat model for the attack is that an adversary has an Oracle IC that is used as a black box to obtain the input-output responses. The algorithm begins by randomly selecting a width that is Wi from the set SW. Next, the circuit response at the selected width Wi is computed. And if the circuit response is less than the oracle mean, that is the target width minus a variation, then constraints are added to look for the width that is less than Wi. Similarly, if a randomly selected with Wi produces a circuit response that is greater than the oracle max, that is the target width plus variation, then constraints are added to look for the width that is greater than Wi. In this way, the algorithm prunes the key space until a width that produces the circuit response in the range of oracle min and oracle max is determined. Then such a width is considered as a candidate solution. The algorithm terminates when all the candidate keys in the search space are determined. Um, the monotonic attack has been evaluated on 4 different circuits and for different PBT variation. It can be shown that for a maximum of 10% PBT variation, a maximum of 132 candidate keys have been returned. So this can be evaluated through a brute force attack. And the most of the attack conclude in order of a few seconds, the longest being 1 minute. The attack runtime does not increase significantly with the key size, since adding additional key bits only linearly increases the number of iterations required by the algorithm to execute. In this section, design insights are provided as a countermeasure to the two proposed attacks and to make analog obfuscation techniques more secure. So the equal key spacing is to thwart the key spacing attack. So the key produce bits of equal spacing has to be ensured. So now the attack requires the same number of iterations as a brute force attack. So which spacing generated by the key must be considered during obfuscation, and the trade-off between the efficiency of the attack and area overhead should be considered in designing the security technique. So the next is generating non-monotonic key dependencies. In this technique, the designer has to make sure that the applied key produces a non-monotonic circuit response. So in this case, obfuscating multiple circuit blocks and combining the keys of the obfuscated blocks produces a non-monotonic function. So this is an example of a CS amplifier where two transistors M1 and M2 are both obfuscated, therefore producing a non-monotonic function. So now the adversary is unable to prune the key space since the oracle response do not match the obfuscated circuit response. Now I will be concluding the presentation. The security vulnerabilities of the key-based analog obfuscation technique have been described in form of key spacing attack and monotonic attack. And the attacks were evaluated on the VCO, CS amplifier, differential amplifier, and operation amplifier for different key sizes and for various exclusion zones. The methodology to thwart the attacks are developed that provide increased security when implementing the analog obfuscation. This is in form of equal key spacing and non-monotonic key dependencies. These are the references used in the presentation. Thank you.